As we've learned, binary or base 2 representation is how computers store and process numerical information. In fact, it's how computers store and process any kind of information, since computers don't know how to do anything else besides math. Everything you do on a computer is the result of some mathematical process performed on numbers written in binary. In the next few videos, we're going to learn how this works on the most basic level, specifically by learning how to do arithmetic, basic addition, subtraction, multiplication, and division using numbers represented in binary. This video focuses on addition, and there will be videos for the 3 other basic arithmetic operations coming up. So to understand how to add 2 binary numbers together, let's first do some very basic review about how we learned how to add 2 decimal numbers together back when we were kids. So let's look at the sum 147 plus 782. The algorithm we learned back in the day goes like this. First, write the numbers vertically, like so. Then start adding in the ones place. Here, 7 plus 2 is 9, so that goes in the ones place for the answer. Then move on to the tens place. Now this time the sum of the digits 4 plus 8 is 12, and it doesn't make sense to write a 12 in the answer for the tens place because 12 is bigger than 10. It overflows the space. So what we do is we write down the 2, which is in the ones place of this digit sum, and carry the 1 over to the hundreds place, where we now have 3 things to add, the 1 and the 7, and the additional 1 from the carry. That adds up to 9, and this doesn't overflow the space, so we write it down. We're all done, and so the answer is 929. So in base 10, all addition is really carried out only on single-digit numbers, 0 through 9, one place at a time. And if we do a digit sum and it gives a result bigger than 9, then we split off the ones digit from the tens digit and carry that tens digit up to the next place and continue until there's no more carrying and no more digits. Adding numbers in binary uses the same principle, and in some ways it's actually easier because you now only have 2 possible digits to work with, 0 and 1, rather than 10 of them. Since, as we just pointed out, addition of larger numbers is really just repeated addition of single-digit numbers together with this carrying process, let's think about what happens when we add 2 single bits together. Well, 0 in binary still means 0, so 0 plus 0 is 0. And 1 still means 1, so 1 plus 0 is 1, and also 0 plus 1 is 1, because addition is commutative, which means that the order of addition doesn't affect the answer. But when we add 1 and 1, it gets a little tricky. The answer, of course, is 2, but remember we are in binary now, so we should write 1 plus 1 equals 1, 0, which is 2 in binary. That means when we add 1 and 1, we end up with a 2-digit number that overflows the space. It's analogous to when we added 8 and 4 in the starting example. We got 12, so we wrote down 2 and carried the 1. Similarly, anytime we add 1 plus 1 in binary, we'll have to carry a 1. Now we're ready to think about how computers add larger numbers in binary. Let's look at 110 plus 11. In decimal, this is 6 plus 3, so the answer should be 9. But we want to do this entirely in binary without changing the representation to decimal, because computers wouldn't make that change. Just like in base 10, line these up vertically like so. I added a 0 on the left side of the second number just for padding to show you how the 2 numbers line up. It's not really necessary. Now, just like in base 10, add 1 place at a time, starting with the ones place. Here, 0 plus 1 is just 1, so that goes in the ones place for the answer. Moving to the next place, which is the 2 place, not the tens place, we encounter 1 plus 1. As we saw above, the answer is not really 2, but 1, 0. This overflows the space, and so we'll write down 0 and carry the 1. Now in the next place we have 1 plus 1 plus 0. Just like in decimal, we can only really add 2 things at a time, and the grouping doesn't matter because addition is not only commutative but also associative. So add 1 plus 1 to get 1, 0, and then add 0 to this to just get 1 0 again. Just as in the last step, this overflows the 1-digit sized space allowed for the answer. So just put down the ones place, which is a 0, and carry the 1 over. And that next place over, there is nothing. You can think of it as 2 zeros if you want. So we would be adding 1 plus 0, which is just a 1, and that goes here. So in the end, we have as the result 1 0 0 1. And in decimal, that is indeed 9, like it's supposed to be. Let's look at another example, 11101 plus 11001. In decimal, this is 29 plus 25, so the answer is supposed to be 54. I encourage you to pause the video and try working this out for yourself before watching the solution. And remember, it's totally fine to make mistakes. You won't really be learning anything otherwise, and nobody's watching you anyhow. So we begin by lining these up vertically and adding place by place, starting with the ones place. This is 1 plus 1, which is 1 0. Write 0 and carry the 1. In the twos place, we have 1 plus 0, which is just a 1, so write that. There's no carry here, so we just move on to the fours place. This is 1 plus 0, which is just a 1, so write that with no carry. Then in the eights place, we have 1 plus 1 again, so write 0 and carry the 1. Now in the 16s place, we have 1 plus 1 plus 1. This is technically 3, but in binary that would be 1 1. This is pretty much the same situation as having 1 0. The 1 1 overflows the single digit space, so we copy down the first 1 and carry the second. That last place there has nothing in it, but you can think of it as 2 zeros. 1 plus 0 is 1, and so that's the last part of the result. We arrive at the answer 110, 110, and if you check it, this is indeed 54 in base 10. So congratulations, you've now learned the basics behind doing addition in binary without translating to decimal first. Now we have to tackle subtraction, and this will happen in the next video.